This is the first lecture where we're going to start to handle more complicated statistical analyses. And specifically, we're going to be going from looking at one or possibly two independent variables to learn how we use multiple independent variables either by themselves or, in this case, to predict a dependent variable using multiple regression analysis. So to review, we've talked about having either a continuous or a categorical or discrete independent variable and a continuous or categorical or discrete dependent variable. And regression is the case when you have continuous independent variables and continuous dependent variables. And if you have multiple independent variables, then that's a multiple regression. If it's a single independent variable, then it's a linear regression. So let's review linear regression a bit. Used to analyze the relationship between two or more continuous, in this case, two continuous variables, two at a time. We use it to look for evidence that the changes in one variable, so the independent or the predictor variable, are related to change in another variable. So the dependent or response variable. The predictor or independent variable is usually denoted x and is plotted on the x-axis. And the response or dependent variable is usually denoted as y and plotted on the y-axis. A significant relationship between x and y does not prove a cause and effect relationship. You can, through good study design, constrain the conclusions that might lead you to have better but not comprehensive evidence of a cause-effect relationship, but it's a good start. So the assumptions here are that there's a linear relationship between x and y, that the response variable and its error term follows a Gaussian distribution, that for any given value of x, the associated y values are independent with an error, that's that little e there, that is distributed as, that's that tilde, normal distribution with a mean value of 0 and a certain variance. We assume homoscedasticity, that is constant variance of errors across all the values of x, and independence of error terms. So the residuals are not correlated in any way. So we start with the equation for a line. You probably saw this relatively early in life. Y equals mx plus b. Well, in this case, we're referring to this as y is equal to beta 0, the intercept, plus beta 1, the slope, times x. Okay, so beta 0 and beta 1 are the parameters of the model. Beta 0, the y-intercept, is just the value of y when x is equal to 0, and the slope is the change in the y variable for each unit change in the x variable. And then we just add on that error term to get the regression model. And that allows us to account for the fact that not all the points are going to fall on the line. So we're going to conceptually start with a line that runs through the middle of a cloud of data. And that data is going to have some mean y and mean x variable. And then we're going to rotate that line until we minimize the sum of squares, the residual sum of squares, denotated here as d sub I, where d sub I is equal to the difference between yi, the observation, minus the estimated y for that particular observation, I squared. So residual sum of squares, yi minus y hat I is the residual for that particular point squared, and then you sum that up. That's the residual sum of squares. And here's an example, and we can see all of our independent little deviations there, denoted as D, D11, D13, D14, D15, and our line. And you can imagine rotating that line so that when you look at each one of those D's, then squared, that sum is going to come to some minimum value. Okay, so now we can state a number of hypotheses. The first hypothesis, HO, is that the slope of the regression line is 0. And that would mean there's no linear relationship between x and y. We didn't see any change in y that's associated with changes in x. Another hypothesis, the alternative hypothesis would be that the slope of the regression line is not equal to 0, that there is a linear relationship between x and y, and that the changes in y are associated with changes in x. Alternatively, you could have a one-tailed test. So you could test whether or not our slope is greater than 0 or less than 0. That is not used very often. In general, we're actually trying to do estimating. So, knowing whether or not there's just a positive or a negative relationship between independent and dependent variable isn't of that much interest. So in R, here's an example of doing linear regression. So we're going to load in some data on production from a table that is located online. So this is a table we have access to online. This is produced as part of a book, and we're going to read it in using read table. And if you look past all the HTTP stuff in pink, we're going to say there is a header, and that the separating delimiter is a space. There's a space between those two quotes. So we're going to read this into a data table, and we're going to wind up with 3 columns in our data table: case, runtime, and run size. So runtime is the time taken in minutes for a production run, and run size is going to be the number of items produced in each run. And we want to be able to describe the production runtime as a linear function of the number of items in the run. Could be very useful to come up with a good relationship. You're going to be able to say, oh, we need to produce 175 of these things, or 275, because 175 is already the first case. We need to produce 275 of these things. How long is it going to take? Something you might want to know. And we're going to use the LM function again. So we're going to fit a regression model using that function, and we're going to call that the variable that holds that model production.lm. And we're going to assign to it, you can see they're using the earlier assignment operator here, LM, the linear model, and we're going to say runtime, we're going to say is proportional to run size. Okay, so that's a very simple model, and we can use those column header names, runtime and run size, because we're going to specify that the data we're going to use is that data table production that we've already defined. Once we do that, we can then get a summary of the results. This is all similar to stuff you've seen before. And the output will look something like this. So what this says is that if you look down at the coefficients, right, that the best estimator of the runtime is 149.75 essentially. So there's some intercept. The minimum time for a run was 149.75, or would be the minimum if you had no items, if you were just doing some sort of setup process. And that run size, if you multiply the number of things you're creating by 0.25924, then that's going to give you the runtime. So that's your equation. The runtime is equal to 149.74770 plus 0.25924 times the run size. Okay. We look at the t-values that are going to assess we're going to use for assessing the probability, and then at the probability, and what we're going to find is that both variables are statistically significant at that 3 asterisk value, which is less than 0.001, so highly significant. Okay, R squared for this is going to be 0.73. When you adjust the degrees of freedom for the fact that when you use an adjusted degrees of freedom, your R squared is 0.7152, okay, which is very good. And your p-value is, again, your overall p-value is much less than 0.001. And you look at the plot, and that all makes sense. That is what we're seeing. This is a well-correlated set of values. Right. So we can then do ANOVA on this in R, which will break down the total variability in the sample into 2 parts. The sample variability, total sample variability, as is equal to the variability explained by the model, the sum of squares of the regression, and the unexplained or error variability, the residual sum of squares. So in R, you can just skip to just getting the ANOVA results by saying ANOVA production.lm, and you get an analysis of variance table. And again, we have 1 degree of freedom associated with the variable run size, and 18 degrees of freedom associated with the residuals, an F value of 48, and probability of getting a greater F value if there was in fact no statistically significant relationship between these variables, as much less than 0.001. So we feel pretty confident about this, as we should. And then R provides you with some functions that allow you to get at important parts of the regression output. So fitted will tell you what the estimate for a particular case is, and residuals will tell you what the residual for that case was. And we can make a new table here, and just by saying data.frame production, the original data table, and giving it new columns. So fitted.value equal to the fitted value of production the fitted values from the production.lm model, excuse me, and a column called residual, which is set to the residuals associated with all the cases in production.lm. I'll make it a nice table. It's good to have. particularly if you want to do, well, if you want to use the fitted values, obviously, but also if you want to do more analysis of how well your model is doing. Okay, now we can talk about multiple regression. So we're going to generalize that simple regression methodology to describe a relationship between a single response variable and a set of predictors, x1, x2, blah, 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 through xp, where p is the number of independent variables that will be fit into a linear function. So for each object that we're describing, for each object in this case is like a case, we're going to have the p explanatory or independent variables and the y response variable. So the model equation here is going to be, your y sub I, for a given case, is going to be beta 0 plus, that's the intercept, beta 1, the first coefficient, times xi, the observed value for 1. So xi1 is for that first variable. So the ith case of the xi variable, plus beta 2 times the ith case for variable 2, blah, 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 all the way to beta coefficient p times the x value for the ith case of the pth independent variable, plus some randomly distributed error. And so what we want to know is beta 0, the overall mean, the intercept, and all of the p regression coefficients. So as with the simpler linear regression, we want to find the equational line that best fits the data. In this case, it means finding beta 0, beta 1, beta p such that the fitted values of y sub I, so or it should be the fitted values of y, but that's just, this is what we have for, a single y would be y sub I given by, so we're going to use that little hat symbol to be the estimate for the ith case as equal to, again, that whole equation. And we're going to do that again by minimizing the sum square of the residuals as calculated just by the original value yi minus the predicted value y hat I. We're going to do this by least square, okay? This is not the only method to do this, okay? And for some problems, it's definitely not the best way. And the remember that, I mean, the most common case is when you want to do something called like an orthogonal regression. And the reason that the least squares method is not always suitable is that it assumes that all of the error is in the y variable, okay? And it assumes that the x's are measured without error. And we know that's not true. And so you sometimes get different results when you are looking at x values that are being measured with some error. The case where I ran into this is with estimating tree height using remote sensing. When you do that, you know there's error in the field, and you know that there's error in the remote sensing estimates. And if you're trying to test whether or not the two methods are equivalent, you don't want to use a method that just assumes that, say, the field values have the error, because you can get different answers. So that's something to just keep in the back of your mind, very, very, very far in the back. So multivariable regression, here's an example. This is using a book weight data set. So we're going to load the data in. We're going to import the library, DAAG. We're going to use the data set allbacks, okay? And then we're going to use the attach command for that same data. And now I have to stop. Okay, so let's take an example of multivariable or multivariate regression in R. Here's an example for book weight. We're going to load that data in. We're going to use a library command to import that library, DAAG. And then we're going to call up the data set allbacks. And then we're going to attach allbacks. And what attach does is it allows you to access the variables in the data frame allbacks, okay, just by their column names. And so that makes it easier to, write equations, and you don't have to go fooling around with all sorts of, $ nonsense. So we've got 4 variables here. The volume of the book. So I guess X times Y times Z. The area of the book. So just X times Y. The weight of the book. Say grams, and then the type of cover it has, either hardback or paperback. So the first thing that one tends to do in multiple regression, no matter what platform you're working on, is to look at the relationships between the individual variables. So here we have volume, area, weight, and cover, and just by saying plot allbacks, giving it the data frame, R knows it wants you to create one of these lovely matrices of scatter plots, and we're saying gap equals 0 so that there's no, it makes it just one cohesive square there and doesn't put gaps in between things. And the way to read these is, if you look at the top line, for all the graphs on the top line, volume is the Y variable, okay? So you just sort of look at volume and you look over to the right and you say, oh, okay, volume is the Y variable there. And then for each of the 3 graphs on the top line, the x-axes are area, weight, and then cover, okay? And so what this has done is create a 4x4 scatter plot matrix. And so every possible combination of variables is being considered here. Now, the plots where you see the words volume, area, weight, and cover logically would be volume versus volume, area versus area, weight versus weight, and cover versus cover. Those are not of interest to us because that's just a 1-1 line. And note that every pairing of variables is produced twice, okay, or presented twice. So in the upper right-hand corner, we have a graph where volume is the y-axis and area is the x-axis. But in the lower left window, we have a graph where the x-axis is volume and the y-axis is cover. So really, you either need to only look at the sort of bottom triangle of graphs, the 6 graphs that are in the area under each one of the words, or all the words, or the top triangle, the same 6 graphs, but inverted with their x and y axis in the upper half in the area above where it's displaying those words. So again, we're going to use the linear model function, and we're going to create a new regression model called allbacks.lm and assign to it the result of the lm function, and we're going to give it a name. We're going to give it a formula, and that formula is going to be that the weight is proportional to the volume of the book and its area. Okay, and we're using those column names and then specifying that data is all back so that we don't, again, have to mess around with specifying each column in the data table independently. And then we'll use summary to test that model or to get the summary information on the model we just created, allbacks.lm. Okay, I want to say one thing about the slide that I just presented. That is that the cover variable has been transformed for that plot, and it's been transformed to either be, I think, 0 or 1, or 1 or 2. Basically, it was a categorical variable that that it just displayed the categories as numbers in order to so that you can see if there's any pattern of relationship with the variable before it. So if you skip back a little bit, or if you think back, you'll see that the cover type is included there as a variable, and it's just sort of been assigned values, one value for each of the 2 classes in that variable, and plotted using that information. But the values assigned to them are not significant in and of themselves, that is. Okay, so let's look at the output. First, it tells us what the call was, then it tells us something about the residuals, and now it's going to tell us something about the coefficients. And it has come up with an equation that the weight of the book is equal to 22.4. I'm just going to truncate the rest of the numbers because, it just wastes time. So the weight of the book is equal to 22.4 grams plus the volume of the book times 0.708 plus 0.47 approximately times the area. And then again, if we look at each of the variables and look at the probability of a larger t-value being associated with the each one of the coefficients, the intercept is not statistically significant, but volume and area are, and they're both highly significant. So, and this is saying that as we go down below the significance codes, you see a line there. It says, the multiple R is R squared is 0.9285, which is a very highly correlated result. And then when we adjust for the degrees of freedom, it's slightly less, but it's still quite significant. And then at the bottom, it gives you the it gives you a value for whether or not there were correlations between the coefficients. And it looks like there was a pretty big correlation actually between volume and the intercept, but that probably just has to deal with the fact that this intercept wasn't really significant. Again, we get fitted and residual values using those two functions, and then add on new columns to our data frame using another data frame command. So it's like we're passing data frame with a data frame, and then it knows, oh, you just want me to append whatever comes next as new columns in the data frame. We can then do an ANOVA on this, and again, we see highly statistically significant. So this looks like it's a good relationship for determining the volume, the weighted books, based on things we already know. Okay, so now we're going to talk about how to pick models when it might not be immediately clear which are the best independent variables to pick for a particular regression. So, when we have a data set, okay, and we're doing a multiple linear regression, we're gonna put in variables, some of which we have high confidence in that they're going to be good at predicting the dependent variable, and some of which maybe they're not. Or maybe they're not by themselves, but in the context of another variable, maybe that variable could become important. That's very often the case, that you have independent variables, one of which, say, is very strongly related to your dependent variable, and another variable that maybe is not as strongly related, but once we start looking at using the two variables together, that second variable does improve your estimate to quite a degree. And so the question is, okay, so say we have n independent variables, how do we pick which ones are the best to use for our regression? Okay, so if we have a lot, right, of independent variables, we're going to try to find the best equation, and generally there's going to be a trade-off here between making a really good estimate of your dependent variable, but then also having a simple model. Because at some point you have to say, well, I can add this variable in, but it doesn't really help that much. And so we kind of need to have rules that allow us to say, okay, when is adding another variable justified? When does it actually help to create a good estimating equation? And so we're often interested in comparing candidate models against each other in some organized fashion. Okay, so for model selection, our objective is going to be to find an equation with the least number of variables that still explain a high percentage of variance in the dependent variable that's comparable to the percentage explained with all of the variables in the equation, should that be possible. But the best equation should also be simple and easily interpreted. And easily interpreted just means having a small number of variables. Fewer the variables, the easier it is to be explained. So you want something to be reliable, and reliability doesn't necessarily increase with a larger number of variables. Especially because, remember, ultimately, we're going to create this relationship, okay? And we're going to try to apply that, presumably, to some other data set, okay? So we're going to train our model here, but we're going to want to apply it somewhere else. In general, the more variables you have in an equation, the more chances you have for differences between the data sets to reveal themselves. Now, under an ideal case, you would have sampled your sample that you're using to create your model would be, would cover all the possible combinations of conditions that you're going to see in your data set that you're going to want to predict from. But that's not always the case. And again, the more variables you put in, the more likely you're going to get a variable that maybe doesn't change in the same way that you saw in your prediction variable. So small number of variables in general is better, okay? So the best equations are a compromise between using a lot of variables to explain everything you can, and a smaller number of variables, which is easier to understand and is going to lead you to fewer problems when you go to apply the equations that you're generating. So you've got a balancing act here between predictions and potentially bringing in bias. Okay. So there are two general approaches to model selection. The first is that you could look at all possible subsets of variables. So given your set of independent variables, look at variable 1, variable 2 independently, variable 3 independently, and then 1 and 2, 1 and 3, 1 and 4, for instance, and 1, 2, 3, 2, 3, 4, etc. So every possible combination of independent variable to explain the one dependent variable. And then looking at the change in how well the model does, a goodness of fit index. Alternatively, you can use an automatic rule or algorithm to select a subset of variables based on a criteria you choose. And that doesn't require any consideration by the user. You just have to provide a criteria for doing the selection. So again, if we have p independent variables, x1 through xp, if you have 3 variables, then, that top equation just uses x1, the next one uses x2, x3, the next one uses x1 and x2, the next one uses x1 and x3, the next one uses x2 and x3, and then the last one uses all 3 variables. So, even with 3 variables, that's a lot of equations to look at, but, that's manageable. So, all possible subsets. Our rule is, or our approach is going to be to given the independent variables, compare all the possible models and use one using a criteria you choose. So you're going to have to think about changes in your criteria versus the number of variables. And one thing you'll want to look at is what are the biologically plausible candidate models. So given your independent variables, you can come up with potential candidate models to compare based on biology and knowledge of your system. So that might be a way that you evaluate different subsets. And then automatic is just using an algorithm. Yeah, because when you have a large number of variables, and there are plenty of things where you might use 20 or 40 variables, using all possible combinations is going to require a lot of time. And you might not have a real basis for including or not including, various pairs of variables or based on biological plausibility. Also, an algorithm may be preferable because it removes potential user biases. So, for instance, I've had projects where I've generated thousands of models and then evaluated them in various different ways. And what I didn't want to do was say, oh, I was going in and just picking the equations that I knew would do better in some later step. I was letting an algorithm pick the equations so that there was no question that I had picked certain equations for any motivation that I had. So what are the decisions you do, or what are the decisions based on to keep a variable or not? Well, it could be based on R square. You could just say, give me the thing that predicts the most R square, the highest R square. Could be based on an F statistic for significance, could be based on a p-value, or it could be based on some other criterion. And the thing about R square and F statistic, and to a smaller degree p-value, is that they don't include complexity. It might be nice to have a criteria that actually included complexity, and we'll see AIC is one index that does. Okay, so the criteria AIC is Ikeiki's information criteria. Okay, and it's based on an approach called information theoretic, an information theoretic approach. Okay, and basically what that does is you're trying to quantify the amount of information that you're actually getting to do your prediction. And the AIC is calculated based on three things: the residual sum of squares, the number of parameters in the current model, and the sample size. Okay, so the AIC is sample size times the log of residual sum of squares minus n times the log of n, sample size, plus 2k. The logs here are actually ways of relating RSS and n to the information contained. I'm not going to get into this. It's all information theory. It all goes back to Bell Labs and their attempts to quantify the amount of information in telephone calls. But just looking at that, the AIC is going to increase with n, okay? All other things being equal. It's going to increase with the residual sum of squares. And it's going to increase with the number of parameters in the current model. Now, of course, our regression is going to try to lower the residual sum of squares, right? But that's going to be balanced against the number of parameters in the current model. So if the reduction in the residual sum of squares isn't large relative to the number of parameters that are required to make that reduction, then AIC will stay the same or go down. So more complicated models means a larger k value, the number of parameters, and in general, you're looking to balance that effect from the little 2k there on the end against reductions in the residual sum of squares. So as you add more parameters, presumably the residual sum of squares is going to go down, but that 2k parameter is going to go up. And what we want is to have the smallest AIC for our model, okay? And that allows us to compare the strength of evidence for a given model. Models within 2 AIC points are generally considered more or less equal. So you wouldn't necessarily get rid of one or the other based on, or another, I should say. There could be multiple ones, just based on a small difference of AIC, where small is, within a couple of points. So the first thing we're going to look at is a backwards stepwise elimination approach. First thing we're going to do with this is we're going to fit a full regression model, the global model, using all of the independent variables we have available. And then, one by one, we're going to remove variables. And we're going to start with the least predictive variable. And the least predictive variable is either going to be the one with the largest p-value or the smallest F statistic. A partial F statistic is just the contribution from a particular variable to the overall F, or the AIC. So we're gonna pick the least predictive variable, and then we're gonna remove it. And then we're gonna repeat that until some level is met. So for instance, we might say, well, if all the remaining variables are significant, then don't remove any more. Or we might say, well, if some level of AIC is met, then don't remove any more. So then there's a forward stepwise selection. So just fit an intercept only model, just the null. So basically that's just the mean of the y value. That's the intercept. And then fit subsequent models to estimate what is gained by adding a variable. Okay, so start with the most predictive one, the one with the most significant or lowest p-value, the highest F statistic, etc. Add it to the model and repeat adding until some level is met. So maybe you'll say keep adding until all the remaining variables are insignificant, not significant, or that you've met some level of AIC, and you may consider some level to remove after obtaining your initial final model. So based on their overall contribution to model fit, you might then take out some variables. So here's an example using mussels. So the question is, what affects mussel species richness across coastal rivers? Coastal rivers are considered isolated habitats that are biogeographic islands, in the sense that if you haven't done island biogeography yet, basically it is the study of what controls diversity on isolated islands, or at least in theory isolated islands. In this case, you can consider coastal rivers to be isolated islands, in the sense that they might have, say, mesohaline conditions, that is, moderate salinity, and perhaps these mussels can't migrate from one coastal river to another because then that requires them to go into the ocean and be exposed to high salinity. So in that sense, it could be an island. The high salinity oceanic water is a barrier to their dispersal, in the same sense that a large body of water in between two islands is a detriment to dispersal. So species richness data was collected at 44 rivers. Independent variables were also collected. The area of the drainage basin, the proximity of the species source rivers. So this is the number of intervening rivers between each basin. Here you have the 4 basins there. Measures of environmental quality, so measurements of hydronium and nitrate, and the amount of dissolved solids. So here you have your table. You're looking at the top of it using the head command, and here we have a variety of rivers and the associated data. And if we plot just the area of the watershed versus the number of species, you can see there's some relationship. It would appear that there's some relationship. It doesn't seem like there are a lot of cases with like very, very few species when you have a very large area. Otherwise, some of these things look weak. We have one thing out here there on the right where you have a very large area, but relatively few species. So that's a potential point against the hypothesis that there's an area-species relationship here. And I should say in island biogeography, the area of the island, because it's isolated, is supposed to be the limiting factor on the number of species on that island. The larger the island, the more species you'll observe. And then here we have this metric of distance between a particular river and adjacent coastal rivers. And now, oh, look at that. Here we have the dissolved solids, which we have this as this residue value. And boy, maybe that explains the fact, you got some points out here with low number of mussels and very high residues. So maybe those dissolved solids are not particularly good if you are a mussel. Okay, so before we do the multiple regression, we're going to look for correlation between covariates. So we're just going to look at the independent variables, the covariates, by extracting columns 3 through 10. We're going to create a table of correlation coefficients using the Pearson correlation. And so each row column will be pair will be the correlation between 2 variables. Let's print that out, and this is what we find. Well, first of all, area is not doesn't seem to be correlated with any of the other independent variables to any significant amount. These stepping variables are highly correlated in the sense that it's a in some cases it's a positive and sometimes it's a negative correlation, but there are the correlation magnitude is large among those variables. And so let's go back. So stepping AC, AP, SD, and SL are for each drainage area the number of streams between that drainage area and a larger regional river, so that are denoted as AC, AP, SD, and SL. And so because they're all distances, if you're between 2 of these large basins, then the distance to one is going to be negatively correlated to the distance from another, because you're going to either be closer to one or closer to the other. If we then look at like nitrate and residual, Organic material and the dissolved materials and hydronium, those don't seem to be very well correlated either with each other or the other earlier variables. So stepping AP and stepping AC are highly correlated. Stepping SL and stepping AC have a high magnitude correlation, but it's a negative correlation. Stepping SL and stepping AP are negative and highly correlated, and stepping SV does not appear to be strongly correlated. So this is all just a question of which their sampling of streams, whether or not you're going to see positive or negative correlations between that stream and these large rivers. So we're going to put on as a constraint, candidate models cannot include all of these together. Okay, so that's going to be an important constraint on what we're going to consider to be a good model. So let's test the covariates with just one at a time. So again, we're going to create a model using LM, linear model, and we're going to start with species as a function of area and do the summary. And what we're going to find is, I'm just going down here, almost to the bottom, you know, the R squared there is going to be 0.2556. You should know by now, you know, go up to the coefficients, it's statistically significant. And we get an AIC of 274. Of course, we want to go down. So let's remember that with AIC. And that's that relationship. So it's saying, oh, there is a relationship there, despite the fact that we've got some outliers at the higher areas. Well, now let's look at a series of independent models using these various combinations of variables. So the first thing we're going to do is we're going to just look at the area. So that was that AIC of 274, and we're using two variables there, with, I guess, the intercept being considered one of those. Now we're going to look at proximity. So using just the pairs of variables that were not highly correlated. So that's going to be AP and SV, SL and SV, and AC and SV. So these are case 3. And we've got lower R squares there, and a higher AIC. So by themselves, not competing with area. Then we can start looking at the chemistry, the nitrite, the hydronium, the residue variable independently. Again, not better than area. I'm looking at the AICs there, 287, 283, 282, and then putting them all together, right? We've got ln EQ, 4 variables, because that's going to be the intercept, the nitrate, hydronium, and the residue. And, you know, it explains a little more variance. It explains 22% of variance, but it's got a higher AIC than the area. Now we're going to go and look at grouping two things together. I'm sorry, 3 things together. So in one case, we're using area and the chemistry variables, EQ. That's going to give us 5 variables, because we got the 3 EQ variables, we got the area, and we have the intercept. And that's explaining 38% of variance, more or less, and has an AIC of 272. So this looks like somewhat of an improvement over just area alone. And then we've got the model that's including area and the chemistry and AP. And AP must be the AP-SV variable, okay? So now we have 6 parameters. Bang, that really does make a difference, right? I mean, now we're up to 55% of variance, and we have an AIC that's 260.7, and that's an improvement of roughly 14 points below just using area. And finally, we have the global model, and so the global model is going to include everything and APSD. Okay. So that variable is going to have 7 parameters, and that explains 57% of variance, which is a bit of an improvement over the last one we looked at there, just using area, APSV, and the EQ. But now let's look at the AIC. The AIC is only slightly better. And so, it's a little lower, 260.0 versus 260.7. We said 2 points we're going to assume is about the same. So the winner, in my opinion, is area EQ AP. Okay, because that last one, the global APSD, must be including the other proximity variables, and they don't seem to be doing a great deal of improvement. So I would say the 6 parameter model explaining 54% of variance with an AIC of 260 is probably the best model. And then here we go again, and we can see the relationship between all the models and, in particular, the AIC, because that's the one that really helps you best compare model fit. So now we can look at the change in AIC, and what we see is, the AIC for the global, that's just 0 because it's just compared to itself. And then removing the other proximity variables, that only decreases it by 0.7. And like I said, we're going to call everything within 2 pretty much the same. And then it's only when you take out the APSV variable from the LM area EQ AP model that you start getting a big increase in AIC. So this is what you ultimately have, a model species as a function of area here at the top line, plus the stepping AP, plus nitrate, plus hydronium, plus residue. And now that we go here, we see that, the first thing I look here is the coefficients, and I say, oh, wait a minute. In this context, nitrate is not actually statistically significant. Okay. And in that case, I would remove nitrate from this equation because it's not doing any sort of independent work that other things aren't doing. Yeah. And so that just shows you that's the estimate and standard error. And we run nitrate alone. It's not statistically significant. You can see there on the right in the coefficient table, it's got a significance of 0.825, so that's not significant. Multiple R square is 0.001, blah, blah, blah. This is not worth including. And so, you should remove that variable. And yet, so if we exclude nitrate from this, we get a model where all of the individual parameters are statistically significant and we wind up with a multiple R square of 0.52, and an AIC of 260.9 versus on the left the AIC of 260.748. So that's a tiny difference, like 0.25. And again, we said that wasn't important. Again, on the left is the model with nitrate. On the one on the right is without nitrate. And it looks like we have not lost very much by removing it. So that's a good last step to do. Make sure that all the individual parameters are actually statistically significant. And that just demonstrates your values. Okay, so then we can add those on as a as the fitted, the residual values. Looks like residual in the line at the top is misspelled, but you know, it was obviously corrected before they put it in this table. So there we go. So what conclusions can we draw? Well, we can draw some conclusions about what is actually important for the distribution of these muscles, and of those, you know, area is important, but the closeness to one particular river seems to also be a big factor. So that doesn't quite fit the whole global island biogeographic model. And water chemistry also seems to be important. So it's a more complex story than just the question of isolation from places where species could migrate. Okay, that is interpretation of a multiple regression.